For those of you who were at my Afghanistan and Mars talk yesterday, you already know about my military background. I'm sorry? Oh. Always. So I'm a 10-year military veteran, United States Navy. I've deployed with the Army to Afghanistan for 12 months. I spent 4 years in Japan, and now I'm a reservist. I transferred to the reserves, and every few years I travel to Hawaii. We do RIMPAC, which is a giant coalition exercise where just navies from all around the world all gather. If you ever saw Battleship, it's the same thing but without aliens and Rihanna. So, but it's pretty amazing. It's pretty fun, and you really get to collaborate with so many diverse cultures. So today I want to show you kind of the other side of what I work on that's not military related. So at Arizona State University. I'm a student of the School of Earth and Space Exploration in Tempe, which is part of Arizona State University. I'm specializing in geology specifically, but I'm mixing in a certificate in Geographic Information Systems, which is GIS, and I'm kind of shaking it up with a minor from the School of Sustainability, and I think that builds like a really good background. One of the interesting things about the School of Earth and Space Exploration is that the systems design majors, the engineering majors, have to take a healthy dose of science, and our scientists have to take a hearty helping of engineering. So including the dreaded Calculus 3 for engineers class that even the lowliest astrobiology, astrophysics, or geology student has to take. But what this forces us to do is have a true integration at the bachelor degree level of the sciences and the engineering. I know you might have heard of, what was it, about a decade or so ago? What was that Mars probe that went, something was in metric and something was in standard, and it ended up, because the scientists were thinking in one measurement, the engineers were thinking in the other, and then it just became the Mars barrier instead of the Mars lander. So I love that. That's kind of what I imagine is the reason why my university kind of went, hey, why don't we just have the scientists and the engineers who are gonna have to work together anyways? Because unfortunately, we can't do all this amazing science with just a pen and paper anymore and a telescope. We have to build massive machines at that level. But it was in this environment that kind of my colleagues and I started thinking about all of the work that goes into building all of, well, this. And by all of this, I mean all of human civilization. Civilization is basically a giant distributed factory. Think of it like that. A factory that builds everything that you've ever touched that's not purely from nature itself. And it's the ultimate seed factory, a machine that makes itself and more. But we're going to get into that in due time. Anyways, we wanted to know how far you could scale that concept down. How far could you pack all of that capability into something that you could take with you to Mars? And why would we want to do this? When we talk about putting anything more than just a dozen people or so on Mars, we realize that the costs of maintaining such a far-flung bud of our global civilization, that doing this completely through Earth replenishment is impossible, 100% impossible. The costs get exponentially large. You can't ship everything, you just can't do it. The current cost to launch a bottle of water like this to low Earth orbit is over $1,000. Just put one of these in low Earth orbit. And Google's Lunar X Prize Foundation cites $80,000 a pound to ship something to the moon. Mars takes even more fuel. And so of course, to keep this expense to a minimum, we'd want to start building some of our items on Mars once we're there. The obvious items for this would be, of course, items like food and water. Greenhouses and drilling into ice and producing liquid water and cracking it into breathable air are all topics for other presentations. But what I want to talk to you about today is all the rest of industry. Everything you need to make clothes and tools, power plants and construction vehicles, a bit of all of these things you can reasonably send out in an early shipment, but very quickly your population goes up, your base expands, and some of the items on Mars are just going to degrade very rapidly due to the environmental conditions. You can't spend all of your time fixing this highly designed equipment sent from Earth. Eventually, you have to make your own steel and glass, your own simple medicines and hygiene products, your own bread makers, ovens, vehicles, tractors, and backhoes. And so you have... So we came across a concept called seed factories. A seed factory can make itself. It can expand and unpack. It can, over time, make more complex items. An everyday lathe is a kind of seed factory. A lathe can about make 95% of the parts it's made out of. With the drill bits and cutting implements, probably one of the only things that you can't make, about the only thing out of reach of its capability. So with a lathe, I can almost make another lathe. So what if I bring a machine that can make the cutting tools? Think about that just for a second. Now we're starting to kind of think about all of the different tools and devices that I can make with just a lathe by itself, and combine that with raw materials. I can start building a whole machine shop, a whole ecology of industrial machines, end mills, CNC machines. And what we, there we go. Now, taking that concept of all of human civilization as a giant factory, can we break that down into individual machines and processes? It turns out we can't. A lot of work has been done in this area here on Earth. The Global Village construction set, which is what you see behind you, is a project by a group called Open Source Ecology. And you can search for them online. A nonprofit founded in 2003. Their goal is to release in open source, meaning the blueprints and the instructions for construction are completely free. The 50 machines, they believe, when combined with raw materials, can build anything and everything that you need in modern civilization. They add to this goal a mission to build these machines with an eye towards the standardization of parts. They look like Lego or Erector set parts, don't they? Right? But if I'm sending 50 machines to Mars and a good set of replacement parts, doesn't it benefit me to try and use the same kinds of bolts and nuts in as many machines as possible? How about the same couple of motor designs? Or just a handful of simple alloys that I might be able to produce there locally to make up all the materials across my whole industrial ecology? You know, I should attempt at least to standardize as much as possible. Not only to reduce the diversity of replacement parts required on hand, but to reduce the amount of specialization that I need in my repair personnel. Or more likely, the amount of training I need to give to each of my colonists on how to maintain the system that keeps them alive. So what does all this look like when it's put together? The tractor that you're about to see, there we go, is designed for earthbound agricultural and industrial tasks and uses a gasoline engine and hydraulic pump contained within a removable steel box termed a power cube. When plugged into the back of the rover, it provides hydraulic pressure and is used not just for the operation of loader arms, but also for the drive system. Attaching additional power cubes in a modular fashion allows for a more complex tool to be added to the vehicle, such as a backhoe or a trencher, a rotor for digging a well, and various other agricultural implements. All of the plans are open source and available for download right now from the internet, and you can build this thing yourself for between $6,000 and $10,000. And remember, this is just one of the 50 machines that are being designed to interoperate with the same power sources, materials, and hardware. The goal of this group's founder, Dr. Marcin Jabowski, he's going to hate the fact that I mispronounced his name, is to liberate small farms and the third world from what he sees as kind of a monopoly on over-designed and expensive machinery. But what I see, with some modifications, is the blueprints for colonizing another world. Back at ASU, I put together a team called Mars Track. It's made up of a diverse team of graduates, undergraduates, and faculty and industry advisors from multiple disciplines. I myself, I'm a geologist, but I'm the head of an engineering team. We have PhD students, master's students, undergraduates, and everything from astrobiology to astrophysics. Pretty much it's everybody in that school right there that kind of comes under the aegis of SEDS. I'll tell you who they are in just a second. But we're taking open source ecology's concepts and we're combining them with cutting edge research, such as the use of ionic acids. These are extremely powerful chemical acids to dissolve Martian regolith simulant that's kind of scraped off a volcano in Hawaii. It's very chemically similar to what we find at the Viking lander sites. And plate out the metals as feedstock for 3D printers and for forges. This work has been done at the Marshall Space Flight Center 2 years ago. We're looking at the recently released Tesla battery technology given to the world for free by Elon Musk and placed in open source. And finally, we're looking at redesigning this project, the open source ecology, from the ground up, kind of in parallel with what they're doing. Of course, we can't use as much hydraulics as them, if any. We can't use gasoline engines. We're looking at things like hydrazine or a combination methane-oxygen combustion engine. We want to redesign this project from the ground up for Mars exploration and development. So we're currently partnered with Arizona State University School of Earth and Space Exploration, SEDS, which is the Students for the Exploration and Development of Space. I'm actually the president of the ASU chapter. We're an international organization of space students in various fields. I mean, we even have, even at Arizona State University, we have a space policy center for lawyers. I know I sound like I'm really pimping my university, but I apologize for that. And we also, we're a group recently formed called Mars Without Borders, which is a collaboration, international collaboration of space scientists, engineers, and people who are interested in going to MDRS and working together to work on these projects. We received a donation of software from Dassault Systems. They make the SolidWorks software. And some of our designs derive from OSE. We won a software suite from Autodesk, which is the makers of AutoCAD software through Indiegogo. We participated in their Maker Challenge in participation with the White House Maker Fair, which is really cool. And we also online, we raised about $2,500 by selling artwork and books, such as I got 12 copies of books from Kim Stanley Robinson, which is, seeing as I grew up reading Red Mars from like age 14, was kind of a big deal when I got that email, a little emotional. And he sent me some of his last old copies of Red Mars, signed each individually, thank you for supporting open source hardware on the space frontier. And we sold those online, and I still have some left over, and a whole bunch of artwork we put together for Indiegogo. In the end, I truly believe that the concept that we have here, we have a winning concept that will see itself on Mars in some sort of form, even if it's not something that we're doing. And when we establish ourselves on the red planet, I want to get building immediately. So, and I hope you guys do too. So Thank you very much. I guess I have
You have 14 minutes.
I have a lot of time actually for questions.
I think people who land will want to get started.
Exactly.
One question, one comment.
Much there.
Kudos for finding somebody else in the wild that knows about the open source.
Yeah.
Yeah. And can a non-student or an alumni or a former student become a member of SEDS?
Definitely. A former student or alumni can become a member of SEDS. You apologize, I'm going to take off my jacket. It's really warm in here. Yes, can become a member of SEDS. You can just contact the closest university chapter to you. You can go to online to seds.com or seds.org. I know ASU seds.common.org I think is operated by me. I need to update the page.
ASU SEDS?
Yeah, I've been working away for a few months, but yes, sir.
What do you see the role of the emerging 3D printing technology to be in what you are working on?
The biggest problem with 3D printing technology, and don't get me wrong, I love 3D printing technology. It's absolutely essential for a lot of really amazing tasks, especially in, like, if we've seen used by Elon Musk in rocket design. We can see how we can build voids inside of aerospace parts so that we can make them lighter than ever before. You can't create voids like that when you're casting a part. One of the downsides to 3D printing is the time. It takes a long time to print something. If you saw that video of that tractor in there, if I want to print those steel beams, that's not reasonable. I can't do that. First off, I don't have a machine big enough, and it would take too long to make those beams. You're going to have some method of forging steel on Mars. You're going to need that. I mean, you can't ship steel to Mars. It weighs too much. It's not worth it. There's iron ore there. So I see 3D printing as a companion to traditional engineering methods. But you can't build an entire factory just out of 3D printing unless you're building very small things. Yes, sir.
Great work. Have you looked at the Mars Homestead project? And have you looked at, is most of your steel initial processing going to be iron carbon?
I have looked at the Mars Homestead project. I'm actually involved in some of the Facebook groups. There are amazing communities online to talk with people who are thinking about these things on every day. I love waking up in the morning and just getting alerts from like the Mars resource. I could give you guys after here, get a hold of me. I'll give you guys all of the Facebook groups that are talking about this on a daily basis, subreddits, which are great resources for communicating with people online about topics and information and collaborating on this thing. As far as the iron production, we're doing some of the preliminary research on it right now. We're going back and actually in my own backyard and on campus, we're building very rudimentary iron and steel forges from scratch, as if we didn't have anything, as if we had all, half the world population had died in a disease or something, and we had to rebuild civilization from scratch. We have to learn because we're taught at such a high level of industry that most of us have no idea where the basics come from. We have to go back and learn it.
Well, off Earth, you're gonna on Earth, oxygen is free and carbon dioxide is cheap. Off Earth, it's the other way around. They're both very expensive.
Definitely.
And so you're gonna need electrical, or you're probably going to use reflectors of some kind for much of your heat, and you're going to want to laser some spots. And
no, you're absolutely right. In fact, one of the things that we're looking at is, in terms of the materials needed to produce those stuff, is something as simple and old as limestone. Limestone itself is absolutely necessary for human civilization, but as we all know, the cliffs of Dover, made of solid limestone, is from tiny plankton skeletons snowing down to the surface of the ocean over billions of years and stacking up and compressed. There are examples on Earth, we think, of non-biologically created limestone. Anytime when you have water, and I'm getting into my geology geek is coming out right now, and you have you have that calcium carbonate dissolved in the water, and then you have the water evaporates. Which, if we had these large oceans on Mars, we're going to see that probably. You have these super solutions and they evaporate, into these layers, probably mixed with percolate. We would probably want to get into that
For their
afterwards.
The first few months you may, not, or first few years you may not be able to find the enough limestone for that, so we may have to do other things, but
Definitely. But limestone's not just used in iron production.
oh, it's
you
a
need
lot of things.
you need it for mortar. You need it for hygiene products to make soap. I need quicklime. I need a ton of different. Limestone is one of those amazing technologies that we discovered, thousands of years ago. We could bake and we can get different things out of it. Catch Me Afterwards is a book called The Knowledge: How to Rebuild Our World from Scratch, which is a thought experiment on how to rebuild your world from scratch, and it goes into that. Yes, sir.
Can you say again what kind of acids you would be using to dissolve the metals?
Sure, there's a project, if you search online, you can find the abstract in a presentation. I'm trying to find the paper. I actually ran into Anthony Muscatello, I believe, he's a NASA chemist that gave a presentation yesterday. He's trying to connect me with Ms. Carr. She was working on an ionics acid project at Marshall Space Center to dissolve Martian regolith into a goop. And then you did this without having to add heat to the system. The acid was so powerful that it did that. And I'm trying to get a hold of the chemical formula. I'm not sure if she's holding that tight to her chest or not.
I think the term you're looking for is ionic liquids.
Yes, so I apologize for that. I am a geologist, not a chemist. I do a very good job. I do a very good job of trying to find intelligent people in the disciplines that I do not understand and surrounding myself with the best people. I do some, and they love to get onto me when I misspeak. So thank you very much. I'm very aware that I do that. Yes, sir.
Yeah, I like the fact that you're going to vary the habitats in terms of several protections from different things, and also standardizing the parts and looking at 3D printers. In terms of the iron, metals on Mars are going to be heavily oxide. So Badescu, I think, has given a nice book, an inventory of what you can use and what you shouldn't try to use.
See, that's the amazing thing about the Ionic Liquids project, is that, and again, not a PhD in chemistry, but the concept is when you liquidize that out, they're also, that what we were trying to do was pull the oxygen out, to use the oxygen, and they were finding out that by varying the voltage, I believe, you could pull out the zinc and then the iron from that goop, and then you could re-protonize the acid and reuse it all over again. I can give you guys examples of the citations for that paper. There's an abstract and a presentation online. Unfortunately, the actual paper is kind of behind a firewall I can't get to.
Yeah, well, the iron is going to be easily accessible.
Yeah,
Some of the other material metals that are there will not be without a lot of energy.
exactly.
The other thing we're looking at is when we land stuff on Mars, the gear ratio is almost 4. So for instance, Curiosity, which is about a ton, it took 4 tons at low Mars orbit to get it down. A lot of that stuff is aluminum and tungsten. So repurposing that.
Exactly.
But that might be another way that one man's trash is another man's treasure.
That's your absolute first place to look for natural resources on Mars. Cannibalize the materials that got you there. Yes?
I'm wondering how the colonists are going to have time to do all this manufacturing and stuff when they need to spend most of their time growing food just to survive.
You're absolutely correct. You're absolutely correct. And there needs to be a lot more research into trying to automate those farms. Looking at aquaculture, like tilapia farming, that's being used quite readily today. I know there's a group I believe in Tokyo, that's trying to do a tuna farm in a tank. Tuna are very, very, very difficult to not just die. When you put them in a tank, you have to maintain a bunch of different parameters on that. Plus, not sure you want to be growing a predator fish anyways. Might be nicer to try a little farther down on your food chain, a lot less energy into it, but tuna's amazing. Yes, sir, in the back.
So it seems, maybe I missed it, but you're talking a lot about the industrial base to manufacture things. But what about our information technology base, the silicon base?
That's one of the problems, and I did not touch on that. You're absolutely right. I never talked about making microchips. I never talked about making circuit boards. Yeah. Oh, man. That's a complex task. It really is. I'm pretty sure that you have colonists on Mars within 20 years. You can likely be building a lot of the basics, but you can't. You're probably for a long time are going to be one of your biggest imports is going to be microchips, controller devices. Software is cool because we can just transmit that. But physically, microprocessors and computer hardware is going to take a long time before a colony on Mars is going to be able to ramp itself up and produce that level of technology.
The simpler ICs and stuff, I think we'll be able to do quite early. The case for Mars does go into doing producing silicon things. He does talk about how to purify silicon enough to where you could do simple, but probably not real complicated.
The great thing about microprocessor chips is that they are very light. So if there's one thing you have to ship to Mars physically, that would be it. Am I out of time?
You've got 2 minutes left.
I got time for one more question.
Yeah.
Yes, sir.
I got a question. Basically, this is taking the level for students now, trying to get them interested in this type of project, because you're looking at this as being down the road. How do we get the student involved in this type of industry thought? I mean, how do we get students to actually want to be a part of the solution?
They need to be hands-on. That's the biggest thing. I've got a bunch of engineers that love getting into the software, love getting into SolidWorks. They love designing these things. But what you find is about 6 weeks in, your motivation starts lagging. There's just an inherent need for an engineer or even a geologist to get your hands on the equipment to be able to build it, even at a small scale, which is actually where you have a lot of good resources. The Lego Mineworks and old erector sets have been integrating electronics and robotics and programming into their toys so that you can actually get all of the basic pieces. And if you're just teaching this in a classroom environment, even at the college level, you can rapidly prototype very basic machines using these already readily available tools. I think that showing them hands-on how they can build it, and then saying to them, if you have a good design, let's see how far we can take this. Can we turn this into a little baby startup? Can we launch a Kickstarter? Can I take your research and maybe get $5,000 in funding from someone? One sponsor can drop $5,000 somewhere, and let's build a prototype. Let's take it out to the desert, you know? Let's actually see your thing going. I think a lot of kids are worried that, and a lot of students are worried that they'll have these great ideas, but they'll never see them physically get made.
Right.
And we like to go out, the ones that are of us that are over 21. I'm 28, but we like to go out to the bars afterwards, after class, and we go and we sit around, and after a few beers, we're like, let's just, not then, but later, let's just go to the machine shop and just start building something. We're just
That's how you lose fingers.
Frustrated that we can't just start making things, and that's probably just youth, but still, we have the passion. We need funding, honestly.
Sure. Makes sense.
So thank you very much.
Thank you, sir.